Alright, so this is going to be 16.1 practice problem. Where the solubility of a gas is gas in water of 0.745 grams per liter. So that's the solubility at standard pressure. Alright, what is the solubility when the pressure of the gas present above the solution is raised to 4.5? So the new pressure is 4.50 atm. Okay? The temperature is constant at 20 degrees. Okay? So first thing we're going to do is we're going to list our knowns. Alright, so S1 is 0.745. That's the solubility, is grams per liter. Pressure 1 is 1.00 atmospheres because it's at standard temperature and pressure. And then pressure 2 is 4.50 because that's what the problem told us. And so our unknown is solubility 2. Okay, the solubility after the pressure has changed. All right, so we're going to substitute in to Henry's law. So Henry's law is that the solubility 1 over pressure 1. So the solubility at this pressure, or this pressure and this solubility, before any changes, that ratio is equal to the ratio of the solubility and the pressure after the change. Right? Now we need S2, so we're going to rearrange this for S2, and that's pretty easy to do. We're just going to multiply both sides by P2. Okay? So then we're going to end up with S2 is equal to S1 times P2 divided by P1. That's just basic algebra. Then we're going to plug in, and we're going to say 0.745 grams per liter times 4.50 atmospheres divided by 1.00 atmospheres. And we're going to plug that all in, and we should get 3.35 grams per liter. So we increased the pressure, and we also increased the solubility. The solubility increased to 4.5 times its original value, which makes sense for a direct relationship. So we increased one thing, and the other thing increased as well. All right. All right. So this is 16.2. This is calculating molarity. All right. So we have a solution is prepared by dissolving 42.23 grams of NH4Cl into enough water to make 500 milliliters of solution. Calculate the molarity. So we list our knowns. So we know the mass of the NH4Cl is 42.23 grams. Okay, and we know that the molar mass of NH4Cl is equal to 53.50 grams per mole. And remember, that's from the periodic table. That's where we got that information. We know that the volume of the solution is 500 milliliters, and we're going to go ahead and change that to 0.5000 liters. Okay, there's that should be there. So there's three places here, so there should be 3 places here. All right. Unknown. The unknown is the molarity. Okay, which the symbol for that is just a capital M. All right. So the mass of the ammonia chloride is first converted to moles. So how do we do that? So we're going to take the molar mass. We're going to take the mass. So we have 42.23 grams of NH4Cl. Always label your stuff. We're going to multiply that by the molar mass. This is grams, so that means I want grams down here and I want moles up here. So we're going to say 53.50, 1 mole. And we're going to multiply across the top, multiply across the bottom. Okay, and that's going to give us 0.7893 moles of NH4Cl. Okay. Then the molarity is calculated by dividing by liters. Note that the given volume has been converted to liters. So we have to have liters up here, all right? Because that's molarity. Molarity is moles divided by liters. So your volume has to be in liters. All right, so then we're going to say 0.7893 moles of NH4Cl. We're going to divide that by 0.5000 liters of water, and that's going to give us a molarity of 1.579 m. Okay? And the molarity is 1.579, meaning that the liter of solution would contain 1.579 moles of NH4Cl with 4 significant figures. Okay. All right, moving on. All right, so this is 16.3 practice problem or sample problem, finding the necessary mass of the solute. So a chemist needs to prepare 3 liters of 0.250 molar solution of potassium permanganate. What is the mass of potassium permanganate does the pharmacist need to make the solution? So we know the molarity, okay? The molarity is 0.250, right? And we know the volume that we need is 3.00 liters, okay? And we know the molar mass from the periodic table of potassium permanganate is 158.04 grams per mole. Okay? And so then we have to find the unknown, which is how much we actually need to make the molar solution that we need. Okay? So first we're going to find the moles of solute by calculating and multiplying molarity by liters. Okay? So we know the molarity is 0.250. And so we're going to multiply that by the fact that we need right. So this is, remember, molarity is moles per liter. So when we say 0.25 molarity, we're saying 0.250 moles per liter. So we're going to multiply that then by the 3.00 liter solution that we need to make. And so now liters are going to cancel out. And that's going to, when we multiply, we're going to have only moles. So 0.750 moles of KMNO4. Okay? So then the moles that we just calculated are going to be converted into grams. So we're going to say 0.750 moles of KMNO4, and we're going to multiply that by, so that's all over 1, and we're going to say 158.04 grams of KMNO4 divided by 1 mole of KMNO4 equals, all right, so now our moles are going to cancel out and we're going to be left with grams. 119 grams of potassium permanganate are needed. Okay, so what that means is when we take 119 grams of potassium permanganate and dissolve it in enough water to make a 3-liter solution, the molarity will be 0.250. Okay, so that's the answer there. All right, it's just basically conversion, dimensional analysis. All right. So this is 16.4, the dilution of a stock solution. So nitric acid is a powerful and corrosive acid. When ordered from a chemical supply company, its molarity is 16 m, or 16 molar. How much of the stock solution of nitric acid needs to be used to make an 8 liter of 0.5 molar solution? All right. So we know that the stock solution for HNO3, we're going to call this molarity 1, is equal to 16 molar. We know that the volume that we need is 8 liters, and the molarity that we want to have is 0.50 molarity, or molar. Our unknown is the original volume, or the volume 1 of HNO3. That is what we need. That's supposed to be a question mark. All right, so the unknown for the equation is V1, the necessary volume of the concentrated solution. So to solve, we know from reading that the mole of one solution is equal to the moles of the other. Okay, so that means, because molarity, okay, the number of moles is the same, right? And we can set up equality between the moles of the solute before the dilution and the moles of the solute after the dilution. And since molarity is moles in liters, then we can say that M1 times L1 is equal to M2 times L2, okay? And because the two sides of the equation are set equal to one another, the volume can be in any units we choose, as long as that unit is the same on both sides. So then we get the equation of M1 V1 equals M1 or M2 V2, okay? All right, and then we can rearrange that to solve for the problem. So that's what we're going to do here. We need to find V1, so we're going to divide both sides by M1. So V1 is equal to M2 times V2 divided by M1. All right, so then we plug in our numbers, and we're going to get 0.5 molar times 8.00 liters divided by 16 molar. So those are going to cancel out. We're going to be left with liters. That's going to give us 0.25 liters, or 250 milliliters. So then that is the answer to the question. 250 milliliters of the stock nitric acid solution needs to be diluted with water to a final volume of 8 liters. The dilution from 16 molar to 0.5 molar is a factor of 32. So it's 32 times more dilute. All right, so this is 16.5, calculating molality. All right, so to determine the molality of a solution prepared by dissolving, so the mass of the solute is 28.60 grams of C6H12O6. Okay, the mass of the solvent, 250 grams, or 0.250 kilograms. And then the molar mass of C6H12O6 is 180.18 grams per mole. All right, our unknown is the molality, which is a lowercase italicized m. All right, so we're going to convert the grams of glucose to moles first. Then we're going to convert the mass of the solvent from grams to kilograms. All right, so we're going to say 28.60 grams of C6H12O6, and that's over 1, times 1 mole of C6H12O6 divided by 180.18 grams C6H12O6, and that's going to be equal to 0.1587 moles of C6H12O6. That's how many moles of sugar we have. Then we're going to take the moles, 0.1587 moles of C6H12O6. We're going to divide that by 0.250 kilograms of H2O, because remember, molality, you're dividing by the mass of the solvent. And that's going to give you 0.635 molality of C6H12, that's a CO6. Okay? And the answer represents the moles of glucose per kilogram of water and has 3 significant figures. Okay? All right. So let's say we want to find the freezing point depression of a non-electrolyte, something that does not form ions and conduct electricity when dissolved. So ethylene glycol is a molecular compound that is used in many commercial antifreezes. An aqueous solution of ethylene glycol is used in vehicle radiators to prevent the water in the radiator from freezing by lowering the freezing point. Calculate the freezing point of the solution of 400 grams. So our mass is 400 grams of C2H6O2, which is the ethylene glycol, in 500 grams of H2O. So the mass of the solvent is 500 grams, which is the same thing at, this is H2O mass, 0.500 kilogram, right? And then the molar mass of C2H6O2 is 62.08 grams per mole. And then we know that the freezing point, or KF, of H2O is negative 1.86 degrees Celsius per molality. Okay? And so what we have to find is the new freezing point of the solution in degrees Celsius. All right? So this is a 3-step problem. First, we have to calculate the moles of ethylene glycol, then calculate the molality of the solution, and finally calculate the freezing point depression. Okay? So, step 1. We've got 400 grams of C2H6O2. We're going to multiply that by 1 mole of C2H6O2 divided by 62.08 grams of C2H6O2. Right? And so we're going to see that the grams cancel out and we're left with moles. So that means we have 6.44 moles of C2H6O2. Okay? Then we have to calculate 6.44 moles of C2H6O2 divided by the number of kilograms of H2O. And that gives us 12.9 molality C2H6O2. Okay? Now we use our equation. The change in freezing temperature or freezing point is equal to KF times the molality. So that's going to be negative 1.86 Celsius per molality times 12.9 . So that's 12.9 molality, and so that's going to give us negative 24.0 degrees Celsius. So the new freezing point then would be negative 24.0 degrees Celsius. All right, so the normal freezing point of water is 0, therefore the freezing point decreases 24 degrees. The freezing point is now negative 24 degrees. That's why you put antifreeze in your car. It lowers the freezing point. It also raises the boiling point so that it doesn't overheat and explode, but it also doesn't freeze and explode because water is weird and it expands when it heats and it expands when it gets cold too.